Hello, in this lecture, we are going to review series and parallel circuits. And we are also going to unlock two very important and useful circuit analysis techniques, namely voltage division and current division. These two techniques are based on the topics that we have just covered. And those topics are KCL, KVL, and Ohm's law. There are some key properties associated with the series circuits. For example, elements in series, they share the same current. Resistors in series can be reduced down to a single resistance. Finally, the value of this single resistance is equal to the sum of the resistors in series. As an example, below I have this series circuit that consists of a voltage source, resistor R1, R2, R3, R4, and R5, forming a loop. And as you can see, intuitively, these 5 or 6 elements, including this voltage source, are sharing the same branch. Okay. Now I'm going to show you mathematically by using KVL, we can prove that this circuit indeed is a series circuit. So what does KVL tell us? From last lecture, we know that KVL says the algebraic sum of all the voltages around the loop in a circuit has to be equal to 0. In other words, the sum of the voltage rises has to be equal to the sum of the voltage drops within the loop. So going back to this lecture notes, as you can see, if I follow the definition and apply KVL, right? So this is my starting point. I start over here, and same thing, this is my endpoint. So I'm going to go clockwise. So I go up to the right, down to the left. And I have to keep track of the sign. So the first sign that I see associated with this voltage source comes with a negative sign. So I have minus Vs. And since we're doing summation, right, the algebraic sum of all the voltages around the loop, I have to plus. So plus V1 plus V2 plus V3 and plus again V4. And finally, plus V5 over here. In other words, Vs can be rewritten and rearranged as such. Vs is equal to V1 plus V2 plus V3 plus V4 plus V5. And by using Ohm's law, I can find what is V1, V2, all the way to V5. As an example, V1 is equal to I times R1, V2 is equal to I times R2, and so forth. This I is the current that flows through each element within the branch. So suppose my current is coming out of this voltage source, and it goes to the right through R1, further to the right through R2, down through R3, and then to the left through R4 and R5, and then back to this voltage source. So this is my branch current that goes through each of these elements. If I combine KVL and Ohm's law, I can rewrite Vs in this way. So Vs is equal to I times R1 which is now used to represent or replace V1, plus I times R2, plus I times R3, and so forth. By taking out the like term, which is this I can rewrite this Vs in this way. So Vs is equal to I times the sum of R1 all the way to R5. Knowing that Vs is equal to I times some equivalent resistance. So therefore, I can deduce that this Rs has to be the sum of all these resistors, starting from R1 all the way to R5. So therefore, I can conclude that this equivalent resistance, Rs, is equal to the summation of all of these resistors in this branch, within this loop. There are some observations that we can make here. For resistors that are in series, they form a series circuit. And they have the same current flowing through them, because this current I, is flowing into each of these resistors. And it's the same current I. And these resistors can be reduced down to a single resistance. In this case, I call it Rs. And this Rs is equal to the sum of all the initial resistor values. So therefore, to simplify the circuit, I can reduce all this R1 to R5 down to a single resistance, which I call Rs. So now I'm only dealing with one voltage source and one resistor. Next, I would like to introduce this very important technique called voltage division. So a voltage division technique is a shortcut for you to find a specific voltage across a series element. So for example, even the same circuits that we analyzed just now, if I want to find voltage drop across R1, which is V1 in this case, I can simply use voltage division to find this voltage V1. Similarly, I can find V5, V4 using the same technique. And that is something I'm going to show you next. Now, this voltage division technique is only applicable if you're dealing with series circuits. And the good thing about using this technique is there is no need for you to find series current. Even without knowing what this current is, you can still use this voltage division technique to find these voltages. It only involves series equivalent resistance and source voltage without the need to find this series current. So next, I'm going to show you some simple derivation to arrive at this voltage division. So V1, this is my V1 here, is equal to IS times R1. I'm just applying simple Ohm's law to kind of get a sense of how V1 can be calculated. But eventually, as I alluded to you, in order to calculate this voltage, you do not need your series current, right? But in the derivation, I'm going to make use of this IS so that I can come up with some useful equation. for this voltage division. So I'm going to say V1 is equal to IS times R1, V2 is equal to IS times R2, and so forth. If I take a ratio, V1, so let's say V1 is the voltage of interest. So V1 over Vs, this is the ratio of this voltage of interest versus the reference voltage, the voltage source. So then V1 is simply equal to IS times R1, which is what I just showed, using Ohm's law, over the ratio, right, over Vs, and this Vs is nothing but IS times the sum of R1 all the way to R5. This is what we derived earlier, right? We were able to lump all these resistors into one single resistor, which I call RS. And RS is the summation of R1, R2, R3, 4, and 5. Okay, so all I'm doing here is taking a ratio V1 over Vs. And V1 is IS times R1. Vs is IS times this. Okay. So now as you can see, IS on the top and bottom drops out. V1 over Vs now depends only on resistor ratio. So if I move this Vs to the other side, now I can find this V1 directly. And this V1 is the voltage of interest, is a desired specific voltage that I wanted to find in the first place. And this is equal to Vs times some ratio of resistors. V1 is equal to this voltage multiplied by the resistor associated with this voltage of interest. If I'm trying to find V1, then I need to put R1 on the top, divided by the sum of all resistors. By the same token, if I want to find V2, all I have to do is replace this subscript 1 with 2. So V2 will be equal to Vs times R2 over the sum. The term in the denominator remains the same. It will always be the sum of all resistors. The only two terms, or the only term that is changing is this guy. Depending on which specific voltage that you're trying to find, you have to use the resistor over here accordingly. Again, if you're trying to find V5, then all you have to do is change this R1 to R5. So now, as you can see, in this equation, there is no series current needed. Okay? We only use series current in this equation here when we try to derive this final equation, right? But you know, eventually this IS on the top and bottom will drop out. Take a look at this example. So I have 100 volts here in series with 500 ohm, 125 ohm, and 375 ohm. If I want to find voltage drop across each of these resistors, I'm going to apply voltage division that we just learned. Specifically, if I want to find V500, which is the voltage drop across this 500 ohm resistor, all I have to do is I take this voltage source, put it over here, multiply by the ratio of this resistor associated with the voltage of interest that you're trying to find, which is 500 ohm, divided by the sum of all the resistors. The sum is 500 plus 125 plus 375. So you do the math, and this is going to give you 50 volts. Next, V125 ohm voltage dropped across this 125 ohm resistor is simply equal to Vs, which is this 100 ohm here, times 125 divided by the sum, and you get 12.5. Similarly, V375 is equal to Vs times 375 over the sum. Now, if you look at the voltage drop across 500 ohm, 125, and 375 ohm, and you sum all these voltages up. So for example, you take these numbers, you sum them up. Do the math, you're going to get 100 volts. So the question is, does this make sense? Does this surprise you? So I'll let you think about it. I add them up, I got 100 volts over here. If I change the question a little bit, instead of putting all these resistors in series, now I'm going to put them in parallel. Even though we have not formally talked about circuits in parallel, but you can kind of visualize that all these elements are connected in parallel. I have 100 volts here, and instead of connecting these resistors in series, I'm going to put them this way: 500 ohm in parallel with 125 ohm, and in parallel with 375 ohm. And the question is, can I still apply the same technique, meaning voltage division, to find the respective voltage? Can I still find V500, V125, and V375 using the same voltage division technique? Clearly, the answer is no. And the reason is, since these circuits are hooked up in parallel, so the voltage dropped across each of these resistors is already known. And that voltage simply is equal to 100 volts. The voltage drop between this point and this point, between this point and this point, between this point and this point, the same as this and that. And the voltage drop across this and this is already given to you, which is 100 volts. Okay. So therefore, voltage division technique does not work for circuits that are in parallel. It only works with series circuits. Okay. So there's one small example here. So if I have 10 volts and 2 times 200 ohm hooked up this way, and I'm going to tap my outputs, or I'm going to tap the voltage right in the middle of these two resistors. And then the question is, what is the voltage if I were to probe between this point and this point? Let's say this is my ground. So from the midpoint to ground, what will be my voltage? Okay. So simply in a situation like this, you can always apply voltage division. And in fact, the easiest way to understand this voltage, what this voltage is by applying voltage division. So once you have done this many times, you realize that if you're dealing with two resistors of the same value, and you're trying to find what is the voltage at the midpoint to ground, then this voltage is simply just going to be whatever this voltage is divided by 2. It's going to be half of what this guy is. Half of 10 volts, which is 5 volts. Okay. So if you apply voltage division, you're going to see 10 times 200 divided by 200 plus 200. And this will always give you a factor of 1/2. So therefore, if you're dealing with resistors of the same value, you will always get a factor of 1/2. So take that times 10, you will get half of what you put in. If and only if you cap it at the midpoint. All right. So now let's look at parallel circuits. So again, there are some key properties associated with parallel circuit. First, elements in parallel share the same voltage. This is exactly the point that I just made over here. Circuits or elements in parallel, 500 ohm, 125, 375, they share the same voltage. Resistors in parallel can also be reduced down to a single resistance, just like series circuits. I can always come up with some equivalent resistance to represent those parallel resistors. Value of this resistance is equal to the sum of resistors in parallel. So as an example, the goal is to simplify R1, R2, and R3 in parallel into one single resistor, which I call RP. P stands for parallel. So I want to come up with some equivalent resistance that I can use to represent R1, R2, and R3 that are hooked up this way. So symbolically, when you want to represent something is in parallel with something else, then you use two parallel bars like this. So this means R1 is in parallel with R2 and is in parallel with R3. Now, instead of using resistance, right, in the last lecture, we talked about conductance. And we know conductance and resistance are opposite of each other. So resistance is the inverse of conductance, or conductance is the inverse of resistance. If you know R, then you know G, right? Because G is equal to 1 over R. Okay. So reciprocal of resistance is conductance. Resistors in parallel produce sum of conductance. So as an example, if I have R1 and R2 in parallel using this parallel bar symbolically, then I know in terms of conductance, G1 and G2 are added together. If R1 and R2 are in parallel, then G1 and G2 are summed together. And this can be used to find equivalent parallel resistance. Instead of using resistance, I'm going to first convert to conductance and then convert it back to resistance again. And the reason, intuitively, is that instead of having to deal with this parallel sign, perhaps it's a lot easier if I can use a simple summation. And this is what I'm going to show you next. So for a given circuit, I have the current source, and I have 3 resistors, R1, R2, and R3 in parallel. As I mentioned, the voltage drop across R1, R2, and R3 must be the same, since they are sharing the same node. This here and this here. So this is one node, this is another node. All these elements are connected in parallel, and they're all sharing the same node. They share the same node over here on the top. They share the same node over here on the bottom. Okay. So whatever the voltage that I have between this node and this node, which I call Vp, has to be the same across all these resistors. So therefore, the voltage drop across R1 is equal to Rp, same as the voltage drop across R2, same as the voltage drop across R3. So this is a very important point. G1, which is 1 over R1, G2, which is 1 over R2, and G3 is 1 over R3. So instead of using R, I'm going to first convert to G. So that is what the reason why we're going to use G1, 2, and 3, okay, for this part of the derivation. So using Ohm's law, let me just write it down over here. So Ohm's law R is equal to V over I. So this tells us that G is equal to I over V. Inverse, right? R is the inverse of G, vice versa. So if I were to calculate I, then I know I is simply equal to V times G. V times G, right? So so I1 is equal to Vp times R1, Vp times G1, and I2 is Vp times G2, and I3 is Vp times G3. So combining Ohm's law and KCL, I have current I. So the current flowing into this node, remember, what does KCL say? The current going into a given node has to be balanced by the current flowing out of the same node. So current going into this node is equal to I, and current leaving this node is equal to the sum of I1 plus I2 plus I3. Okay. So if I combine KCL and Ohm's law, so this current I has to be equal to Vp times G1, which is I1, which is this current flowing out of this node, plus I2, current flowing out of this node, which is Vp times G2, plus current I3, which is Vp times G3. Again, taking out the like term, Vp, factor it out, I have I equal to Vp times G1 plus G2 plus G3, where I call the summation of G1, G2, and G3 GP. GP means parallel conductance. So GP again is equal to the summation of these 3 terms. So in other words, if I know R1, I know G1. If I know R2, I know G2, right? Because all I have to do is I take the inverse. And if I know G1 and G2 and G3, I know what GP is. So GP Gp is equal to the summation of these three conductances. And this is nothing but 1 over Rp. If Gp is the parallel conductance, then Rp is just the inverse of that, and vice versa. Okay. So Gp in terms of R is just 1 over Rp. So what is G1, G2, and G3? Well, that's what we just did over here. We say, if we know R, we can know G. If we know G, we can know R, right? The relationship is just reciprocal. So G1 is equal to 1 over R1, G2 is 1 over R2, G3 is 1 over R3. So now you have this interesting result. In terms of conductance, Gp is just a simple summation. In terms of Rp, what I'm showing you here, this is not Rp, this is 1 over Rp. So that means Rp, if I were to solve for Rp, is going to be, I need to get rid of this 1 over, right? So I have to do 1 over, take the inverse again on the other side, okay? So this Rp is going to be 1 over R1 plus 1 over R2 plus 1 over R3. And now I can say R1 is in parallel with R2 and is in parallel with R3. So that is the reason why, depending on the context, sometimes it may be easier to work with conductance, right? Because all I have to do is to take summation, G1 plus G2 plus G3, instead of 1 over something plus 1 over something else and so forth. Right? Mathematically, this looks a little bit more complicated. But symbolically, right, all we have to do is put 2 slashes representing 2 elements in parallel. Okay. So again, if I have 2 resistors in parallel, you can always go ahead and use this equation to calculate the equivalent resistance, Rp. So if I give you a value here, R1 and R2, you can just plug in 1 over R1, whatever that value is, plus 1 over R2, whatever that value is given to you. Okay. So one technique, one quick trick that I wanted to introduce here is that if you're dealing with just 2 resistors in parallel, instead of using 1 over R1 plus 1 over R2, all you have to do is you can use this product over the sum rule. Product over the sum. That is, you take the product of R1 and R2 over the sum R1 plus R2. Okay. So product on the top and sum on the bottom. And mathematically, you can show that it's the same as 1 over R1 plus 1 over R2. And notice that this technique does not work if you have more than 2 elements. For example, if I have R1 in parallel with R2 in parallel with R3, then you cannot say you're going to do this. R1 plus R2 plus R3. Okay, so this will not work. Okay, this will not work. This trick only works if you are dealing with 2 resistors in parallel. Strictly speaking, 2 resistors only. If you have more than 2 elements, more than 2 resistors, what you can do is you go back to use this equation. Right? For example, you're dealing with 3 resistors. Then you go back and use this equation, or you use this trick twice. So you can first calculate R1 in parallel with R2, and then you get one number, and then you take that number and make it in parallel with R3, and then you apply the same technique again. In that case, it will work, but you have to do it twice. Okay, so next I wanted to talk about current division technique. Another very useful and important technique that you'll find throughout this course. So current division is a shortcut to find a specific current through a parallel element. And this technique is only applicable to parallel circuits only. And just like voltage division, in voltage division, there's no need for you to know your series current. By the same token, this is basically the duality of voltage division. There's no need for you to find parallel voltage. All you have to do is use the current and the parallel resistance to find the specific current through a specific element. And this is the technique that I'm going to show you next. Starting with the derivation. So I'm taking the same circuits from before. I have current source IP in parallel with R1, R2, and R3. This is a node that is shared by these 4 points, or this part of the branch. This is another node which is shared by all these different terminals associated with each element. So I1, current I1 passing through R1 is equal to the voltage drop across these 2 nodes, which is Vp, and is always Vp, divided by R1. Right? This is just simple Ohm's law. V over R is equal to I. I2, same thing, Vp divided by R2. I3, Vp divided by R3. This is basically relative. IP, this is my IP. IP is equal to Vp divided by Rp. Remember, Rp is my equivalent parallel resistance. Simplifying R1 in parallel with R2 in parallel with R3, right? So that's why I wrote it this way. But we know this is Vp. This is just Rp. And we know that from the earlier derivation, Rp is nothing but, right, in terms of resistor, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So let me quickly remind you, Rp, or R1 in parallel with R2 in parallel with R3, can be found over here. Basically just took this part, copy and paste. Over here. All right, so then mathematically I can rewrite this way. So Vp times 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so now I'm going to simply just take a ratio, just like before. So for example, if I'm interested to find I1, this is the current passing through resistor R1, which I call I1. If this is the current that I'm interested in, I'm going to take I1 divided by IP. the simple ratio, current ratio, right? And where I1 is Vp over R1, simple Ohm's law, divided by IP. What is IP? IP is what we just derived, which is Vp times this whole thing here. So now, again, Vp and Vp cancel each other out. So all I see is 1 over R1 over 1 over R1 plus 1 over R2 plus 1 over R3. So in other words, if I want to find I1, all I have to do is I move this IP to the other side, which will give me this equation over here. To find a specific current I1, in this example, all I have to do is I recognize that specific resistor, put it over here on the top. But it's not just R1, it's 1 over R1. It's 1 over R1. Since we're dealing with current, so we take V over R. So we have 1 over R1 after these VPs are canceled out. So 1 over R1 remains on the top, divided by 1 over R1 plus 1 over R2 plus 1 over R3. And this can also be expressed or simplified into IP times R total divided by R1. If you recognize R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, then I can simply just take this 1 over this whole thing, and I can replace it with just R total. But of course, I still have this R1 on the bottom, right? So I bring this R1 down over here, right? So mathematically, these two equations are the same, right? All I did here is I replace R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. That's all I did. Okay. So instead of writing so many 1 over, something, right? I'm just going to keep it simple. If I know R total, take that R total divided by the resistor of interest times IP, then I can find the specific current that I want. Instead of using resistor, I can also use conductance, right? Remember, we did this exercise earlier. So instead of using 1 over R1, I can replace that completely by G1. Instead of using specific resistor, I can use specific conductance, which may be easier for some of you. Okay. So all I have to do here is I take G1 on the top, divided by G1 plus G2 plus G3. Specific conductance over the sum of all conductances. Take this ratio times IP, you will get I1. Now, if I want to find current I2, which is the current passing through this resistor R2, what do I have to do here? Well, all I have to do is I change the subscript from 1 to 2, change this guy. Instead of G1, I change it to G2, over still the same G total, which is the sum of all these conductances. Your denominator will not change, only the numerator. The numerator will change depending on which specific current that you're trying to find. Okay. So let's wrap up this part of the discussion with this example here. So suppose I have a current source, 10 amp, and in parallel, I have 20 ohm, 30 ohm, and 40 ohm resistors. So I'm going to find I1, I2, and I3 flowing through each of this resistor. And the equation, the formula I'm going to use is this guy over here in the middle. So I'm going to use whatever the current from the source multiplied by R total divided by the specific resistor corresponding to the specific current. So my task here is to find what is R total. So what is R total in this case? Well, remember, R total is equal to 20 ohm in parallel with 30 ohm in parallel with 40 ohm. So this R total, basically RP, where RP can be calculated as 1 over R1 plus 1 over R2 plus 1 over R3. That's the equation that I'm using. So 1 over 20 plus 1 over 30 plus 1 over 40, and that will give you 9.2 ohm. And using the formula, I1 is going to be IP times R total on the top divided by specific resistor, right? Which I'm just going to say R1 here. Right? So if I call it R1, R2, and R3, so I have IP, which is 10 times R total, which is 9.2, divided by R1, which is 20. 10 times 9 divided by 20 gives you 4.6. And by the same token, I2 is equal to IP times R total divided by R2, where R2 is 30. That gives you 3. And lastly, I3 is equal to 10 times R total, 9.2 divided by 40, which is R3. And that gives you 2.3. Okay. Now, if you look at I1, I2, and I3, and you sum them up. So I take this, sum them up. This is going to give me an M. Is this something you expect? Does it seem surprise to you? Let you think about it. All right, so lastly, I1 can also be calculated this way. So instead of using the second equation, let's try using the first equation. So the first equation says I need to take 1 over the specific resistor divided by 1 over R1 plus 1 over R2, okay. So by following the same equation, if I want to calculate I1, I take 10 times 1 over R1, 1 over 20, over 1 over 20 plus 1 over 30 plus 1 over 40. And this will again give me the same answer, 4.6 for the first current, I1. Okay, so I invite you to try using the same equation for I2 and I3, and you're going to get the same answer. Before I conclude this part of the lecture, I wanted to switch over to my OneNote and show you something. Okay. In your homework solution and in various parts of the lecture notes, as you will see, I like to use a slightly different technique when I calculate so let's say this is R2, this is R1, this is I. I like to use a slightly different technique to calculate the branch current. So, so suppose I call it I, and this is I1, this is I2. So let's say if I want to calculate I2, which is the current passing through this R2, we can do I times 1 over R2 divided by 1 over R1 plus 1 over R2. Okay, this is one way. Or we can do I times R total divided by R2. Or I can do I times G2 over G1 plus G2. Okay, so these are the three equations that we discussed, and I basically plugged in this circuit. Okay. Now I'm going to show you another quick and easy technique for you to calculate this I2, and which may not be the same as one of these equations or these equations. So I2 is equal to I times, instead of taking 1 over R2 or R total or G2 on the top, I'm going to take R1, put it over here, divided by the sum. So I2, this current passing through R2 is equal to the current I, whatever this current is, times this resistor, which is not the resistor with this I2 flowing through, but is the resistor associated with the other branch, right? I have two resistive branches here. So instead of using R2 on the top, I'm going to use R1 over here. And in the denominator, I have R1 and R2 come together. And this looks very much like the voltage division technique that we saw earlier, right? But notice the difference here is that this resistor on the top is not associated with this branch of interest, but is the other branch. Then the question is, why is this equation valid? So this is one question that I want you guys to think about, and I'm going to give you a hint here. Again, this technique only works if you're dealing with two resistive branches, R1 and R2, right? It does not work if you have multiple branches, right? So you cannot apply this blindly. Okay, this is only good if you're dealing with two resistive branches, R1 and R2. So this is R1, this is R2. So let me put down some numerical numbers as a hint for you guys to think more about it. Okay, so let's say I is equal to 10N. Okay. And this is I2, sorry, this is I1, this is I2. So suppose R1 is equal to, I'm not going to use 10, I'm going to use, well, let me change this number here. I'm going to use 5, and I'm going to use 10 here. Easier. And R2 is equal to 1 ohm. Okay. So I2 is equal to I1, or sorry, I times R1 over R1 plus R2. Okay. And if you plug in the number here, so this is going to give you 5 times 10 divided by 11. Okay, so I'm going to leave it over here. Okay, I'm going to leave it to you to figure out whether this makes sense or not. Right, I'm taking this ratio. Okay, I'm taking R1 and put it here as my numerator. And notice that I chose the value of R1 and R2 in such a way that R1 is much bigger, right? It's at least 1 order of magnitude larger compared to R2, right? In engineering or in electrical engineering, if one is larger than the other one by 10 times, right? And you know that there's an order of magnitude difference, right? So we say that this guy here is much larger than this guy. So 10 versus 1 ohm, okay? So based on this equation, right, I'll let you figure out whether this makes sense or not, and we can discuss this next time.